Welcome to a lesson with Dr. Powell. Let's take a look at the last video that we had where we came up with matrices for the boundary maps. This one from edges to vertices and this one from faces to edges. All right, we can look at these and find their Smith normal forms and find information about it. For this one, let's concentrate on its kernel. It has dimension 1 if we're thinking about column interpretation on both of these. So this one column of zeros tells us the dimension of the kernel is 1. Here, for this guy, the dimension of the range is 1. Now, it's interesting to note one thing. The range of partial 2, so the range of the boundary map from faces to edges right here, let's think about what that is. So we have in fact, you can see it's just the column space here. It's basically just kind of a path going here, here, and then against C going that way. So negative C coming down. So you have an enclosed path. Now, what happens if you take a path which is enclosed like this and you take the boundary of it? Well, let's just think about this one example. So the boundary of each edge in particular, so this one right here is W minus V. Going this way, it's U minus W, and this one coming this way is V minus U. Notice what happens when we add all these two things together. The V's cancel, the U's cancel, the W's cancel, you get 0. In other words, this boundary of edges of a face is actually, if you take the boundary of it, you get 0. It's in the kernel of boundary 1. So the range of boundary 2 is actually a subspace of the kernel of boundary 1. So this guy actually lives in there, meaning that the quotient space of this guy over that guy, so the kernel over the range, will have dimension 0. There'll just be one single object in it. What information does that give us? Let's think about what the kernel of boundary 1 means. The kernel of boundary 1 is actually all nice, simple closed loops like this that maybe start from somewhere. All right, so we have nice closed loops that come around, right? And this is telling us that that of all the classes of nice closed loops, right, that that each one of them is kind of like the boundary of a face. So if I have a face here, it's kind of like the boundary of it. So and in particular, okay, so we have, because these two guys will be the same, like anything that's in the kernel here, so any closed loop will be like the same as the boundary of a face. Now, sometimes if something's a boundary of like a face or a nice region, we can say that perhaps we can deform it across the face all the way to the bottom. So basically, if you have like a string pulled out right here, you could make a rubber band, something that's stretchy, you could like decompress it or whatever, or push it against a cross, so that like continuously any closed loop starting from a point can actually deform outward and inward down to the base, meaning that there's only really one class of simple closed loops on the surface of a sphere. If you just put a circle down, you could easily squash it into a point. Now, if you were thinking about on a donut, you couldn't really do that because you could wrap around this way. You could also wrap around this way. That's two separate different loop paths that you can get. Actually, the number of loop paths that you get is a nice way of distinguishing characteristics and properties, or kind of taxonomy of different types of surfaces. A sphere in this case, it would just be pretty simple on what you get. Everything is completely collapsible to nothing, especially if the rope is infinitely stretchy and compressible and compressible. So that's the information that we can get from these particular maps when we're looking at a sphere. Thanks for watching.